How are we doing on time? So it's 7:30. Excellent. So my fellow sort of coordinators on the team, I've made co-hosts as well as our guest tonight, Julian Onions, Dr. Julian Onions. Chris, if you see anyone knocking in the door, if you wouldn't mind letting them in, that would be great. Okay, and so let's kick off without any more ado, hopefully. So if I go for screen share, have I got sound? I got a bit of sound. Let's see if it actually works this time. So last time I was speaking, what happened? I think my video stopped halfway through and no one told me. So if my video goes out or stops it, let me know. That would be great. Thanks very much. Or if it's actually really boring, just let me finish. That'd be great. Okay, so welcome to Bath Astronomers. It's our monthly gathering. I believe it's March. We're whizzing away through 2021. And tonight we welcome our special guest, Dr. Julian Onions. And he's going to talk to us about Aperture Fever and strapline, does my mirror look big in this? So I'm looking forward to that. Let's just click on the presentation so it should work. Bing. So the usual slide. This is what our society is all about. We've got 44 odd members at the moment. You can see us on our website. You can email us at any time. We do quite a lot on Facebook. Not so much on Twitter, but we're being dragged into the 21st century slowly, kicking and screaming. And last Wednesday of each month is when we meet up, September through to June. And our organizing team is shown brightly down there. And even though I keep offering Chris the opportunity to replace his photo, he never sends me a new one. So he's got the grinning man by the beach, which is great. So we've got Abby, Chris, Jonathan, Mike, and myself that meet up once a month before our meetings and just make sure that we've got a plan for what we want to do going forward all the way through to next year. And we're coordinating on things like outreach, what to do in terms of helping people out, sort of events, all that kind of stuff needs organizing in the background. And so that's your team of 5 that help sort all that stuff out. So if you've got any ideas, either just send us an email on that hello at Bath Astronomers, get to us by Facebook, or if you've got our individual email addresses, then you can just do it to any particular member of our coordinating team. So if you did Simon at bathastronomers.com, you get .org.uk, then you get me. And likewise, everyone's got email addresses. I'm not sure they're all working, but we'll never know. Let's go for hello at Bath Astronomers, and that's probably the best one to go for. What's happening in terms of just organizing around the society? Just we're actually creating some sort of astro short videos at the moment. We thought as a coordinating team, we did that little survey and a number of people asked for specific help on things. So we've got a little list, and we have our Italian art director, Chris, who's helping us out doing little 5 to 10 minute video shorts on sort of the general stuff. You can find it all on YouTube anyway from different sources, but we're going to have our little slant on it. So we'll be putting all of those as we produce them on the Bath Astronomers channel on YouTube. So we've got a couple of on there already. And we do quite a lot of emails, but we don't have something you can sort of print out and carry away, because some people do like that. So we'll produce a newsletter as well. You can read it electronically if you want or whatever. So in the coming months, the Bath Astronomers newsletter will be coming out. Just effectively all those pointers, and if you miss the emails, if you miss the tweets or things like that, it'll be the newsletter is the one place you can always go to catch up on stuff. We haven't had one to date, so we think it's a good idea to do that. Okay. So let's go for some good news for 2029. It looks like Apophis isn't going to hit us. Well, we kind of knew it wasn't going to hit us in 2029. And we kind of had a good feeling for 2036, but we weren't so sure about 2068. But in the last last month or so, 2 radio telescopes have effectively sent a radar beam out to Apophis, done a couple of measurements. One's sending, one's receiving. So it's kind of doing what Arecibo did in one, but that's the Goldstone Deep Space Communications Complex and Green Bank Telescope. they collaborated, and they've worked out that Apophis isn't going to hit us for the next 100 years or so. So we're safe. And here's some of the pictures that were taken via that radar. So these radar images, and if you squint a bit, you can almost imagine what's described as the peanut shape of Apophis. So that's all really good news, and it probably means this isn't going to happen.
Hang on, Nathan. Seek shelter immediately. Seek shelter immediately.
So if you've got a boring moment, then go for Greenland. That's available, I believe, on Prime. And if you have a look on here, you can see Greenland on the left. Why did the Americans always blow up Europe first? I've no idea, but that's where the comet struck in Greenland. Oh, that's a bit of a spoiler if you want to see the movie, but it was always going to happen. Okay, so what can you actually have a look at this month, which isn't Apophis whizzing past? Well, we're moving out of the winter constellations. We're well into the spring constellations. And so around about 8 o'clock, this is the view you'll get. So you've got Leo straight in the south, all the wonderful deep sky objects in and around that to have a look at. You've got the tail of Leo pointing down to Spica, bright star in Virgo. You've got Arcturus, which is even brighter. You've got Ursa Major, pretty much dead ahead. And as you come into the early hours, you've got the wonderful shapes of Hercules, and you've got the summer constellations coming up. So that definitely proves it's spring with the summer triangle that we've got with Altair, Vega, and Deneb coming up. So if you can see those, we're definitely in a nice position for summer. Okay. So there's still lots to see. And there's also stuff to pick up on the internet as well. So about a week or so ago, the protective shell dropped off the bottom of Perseverance, Percy, and that was a protective shell around our little helicopter. And in the last couple of days, this has happened. So it's rotated round. It's dropped 2 of its legs, and then it's dropped yesterday. I think it was all of its legs are down. So it'll disengage over the next few days, and then by about any time from April the 8th onwards, they'll have moved Percy to about 100 meters away from where Ingenuity or Ginny is. So we've got Percy and Ginny, so we just need a few more Weasleys up on Mars and we'll be sorted, but we should be able to see our first helicopter flight on another planet, which will be kind of fun. Hopefully it won't go the way of SpaceX's Starship SN11, but at least SN11, if you didn't see, had a wonderful crash, but it did it in the fog, so you don't really get to see much. But this one we should get in full HD a few hours after the initial flight. And there's cameras also on the helicopter, so if it actually survives, we'll be able to see it taking a real photo of Percy rather than what we saw on Percy and Curiosity, which is it took selfies but took one half of a picture, rotated the arm around and took another part, and then you glued them together. This will be a real picture of one of our craft on another planet, which would be great. There's an event that's occurring on the 12th. So for the early hours, just before it's actually, you've got Callisto here, and a shadow is going to pass in front of Callisto, and that's going to be really close to the horizon, just at sunrise. But if you are available and you have a great easterly horizon, then you can see, if you look at the Galilean moons, you'll see that Callisto dims for a 20-minute period between about 5:20 and 5:40. So that'll be a little bit of fun if you want to watch something dimming in the sky. And another one that's just as the moon's coming to set on the 18th, it's going to be just going across M35. So if you want to see it across the open cluster, if you're quite clever with your photography, you might be able to get a reasonably good high dynamic range shot of the two going together. But as you see this coming up now, that's the trees on my stellarium view. And so we're only a few degrees above the horizon. So you'd need, again, a pretty good view to be able to get that, but it's happening. So you never know. If you're like me and you do like your clair obscura, your weird shadows on the moon, here's one that I haven't got before, which is the Loch Ness Monster. So this is in Ptolemaeus crater. There's a ridge on the edge of the crater, which creates a big bump. in the shadow across the crater floor. And there's also a little craterlet inside the crater, which the edge of it shines white. So you get this effect of a neck within the crater. So on the 19th of April, around about 10:30 at night, you should be able to see this on the Terminator. So fingers crossed. I'll be having a go at it. I had a go at the X and the V the other month, so I'll see if I can get a more detailed photo than this one by Joe. That'll be good. And other things to look forward to in April, we've got the Lyrids. It's not perfect with the moon, but the peak is on the 22nd of April. So it's worth having a go. It'll be a waxing moon, 10 days old, so it'll be quite bright. But the Lyrids have some reasonably bright ones. And if you waited until after midnight, as you normally would do on a meteor shower, the moon will have less of an effect on the Lyrids. So it's worth getting out to have a go and see if you can catch any here. The shower starts on the 26th of April and goes through to the 25th, but as I say, the peaks on the morning of the 22nd of April. So worth trying to have a go there. But I did say there's lots of deep sky objects all around Leo, so definitely worth having a snap there, or even with the milder nights, although I say that I got cold the other night, but with the milder nights, then it's quite a good time to go out and start learning some constellations. So it's a different set of constellations because we moved into spring, going on into summer. So have a look, see if you can work them out, take your star charts and your red light out and see what you can work out. So that'd be great. We did get contacted in the last week or so regarding this, which is the Museum of the Moon. And we knew it was going to Wells Cathedral in November of this year for a few weeks. We've now had it confirmed that it's coming to Bath Abbey from the 22nd of November to the 27th of December. And the Abbey's actually contacted us, their outreach team, and asked us if we can supply volunteers to guide people in and around the area of the moon. So effectively, I said yes immediately. So that'll be a great opportunity. So I sent an email out about people that wanted to volunteer to help out. It would be on Mondays and Sundays in that period. So those are the ones where it's going to be open up at night and you'll have the most effect of the interior lighting. The spooky lighting that they like to do on these events, as well as the contrast with the moon. So it should be most beautiful during then. And we have the opportunity to be there as much as we want between 6 and 9:30 of an evening. So we'll get a group of volunteers together. We'll train them up just so that you feel confident talking about the moon. You don't have to be an expert, but just more than the general public. And we'll have a bit of background reading as well. And that should be a lot of fun. So if you haven't volunteered already, please just drop me an email. We've got tons of time. And the only caveat really is it's just going to be, it's just based on how the COVID situation improves. But the one benefit of the Museum of the Moon is you can make it reasonably COVID secure in terms of in one way, social distancing, out another way. It's just you don't get to pause so much underneath it, which would be a little bit of a shame. But we'll see how that progresses. Okay, so that should be an exciting end to the year. So I'm looking forward to that. But more importantly, what's happening next month? Well, we've got Mary McIntyre coming to see us, coming to see us virtually. And we did a little vote online, and from all the responses we've got, we've selected constellations, mythology to modern day. So she's going in a month's time. She'll be joining us on Zoom to take us through that. She sends in her bio about her fascination with astronomy, and she said one of her first books was the Ladybird Book of Constellations and Their Mythology. So there's a good chance we're going to get a Ladybird book. But Mary is an amazing artist and photographer, so I'm sure that even if it is the content of the book, I'm sure it'll be much more, but I think the artwork that's going to follow it and how she's interpreted some of the wonderful things up in space is actually going to make it really amazing for us. So please spare some time to come along to that. So without any more ado, I've been talking for my usual 15 minutes. I'd like to hand over to Dr. Julian Onions. He's from the University of Nottingham. And I understand, Julian, you spend most of your days doing computer simulations, trying to work out how this big old universe was formed. And fingers crossed, your simulations look a little bit like what the astronomers see. Is that right?
That is the essence of it, yes.
I'm sure it's much more difficult than that.
Not really. A couple of Excel spreadsheets and you're away. Yeah.
But all the influences, all the modeling you have to do, all the halos for dark matter, all that kind of stuff. So I don't know how you keep it in your brain, but
It's all on
excellent.
computer.
Oh, on the computer. So we're not going to ask you about that tonight, but we're going to actually let you tell us all about big telescopes. So over to you. Aperture Fever. Does my mirror look big in this? So I'll stop my share and over to you, Julian.
Pick the right one. Can you all see that?
Yes.
Yes.
Oh, fantastic. Right. So that's a good start. So yes. So this is kind of about telescopes and aperture fever, and in particular professional telescopes, and why we like them so big. Although I'm sure you all like telescopes to be as big as possible. And this is actually an image of the LSST, which has since been renamed the Vera Rubin telescope. That's the mirror under construction there. So nice big mirror. So it could also be subtitled that technology leads to breakthroughs, because pretty much all current breakthroughs, they kind of come about most frequently when we make a big jump in technology, when we go to the next level. And that's been true across the centuries, which I'll cover very quickly before I get on to the main event. So things I want to cover is, why are they so big? Why do we like big telescopes? What's the technology we're using? And what are we going to do next with them? So I guess you all know, just heard about constellations. So that was really what early astronomy was about. And it didn't proceed very much for many thousands of years, really. People had identified constellation patterns, they'd identified planets, and a few other bits and bobs, and made a few predictions. But really, there wasn't very much progress in the sort of science of astronomy at all. It reached its sort of naked eye peak with Tycho Brahe, who had this huge sort of protractor-like thing, which he used to make very precise measurements of the stars he could see, and sort of track their progress. And Copernicus and Kepler and people like that used his results to work out some of the heliocentric picture of the solar system. But really, they were kind of right at the edge of what they could do at this point, and they really didn't get very much further, because there's just only so much you can do with the naked eye. Even small additions like this don't really help. And then, of course, we had the big breakthrough, which was the telescope. And this is a sort of a conceptual picture of the modern day refractor, one with two lenses, and certain issues with it, but perhaps skate over those a little. But they really turned the science of astronomy on its head in a matter of just a year or two. So famously Galileo, although there were others that were also involved, with a very modest telescope, maybe sort of 5 to 10 times magnification, he made just huge leaps. He famously discovered the moons of Jupiter and saw that there were things orbiting around other things rather than everything coming around the Earth. He saw there were mountains on the moon. He saw sunspots. Just a whole new era sort of opened up just on the basis of this one small instrument. So it makes a huge step forward. So that's his pictures of the moons of Jupiter going round. Saturn was just about beyond his reach. He could see there was something going on with it, but he never quite pinned it down. But as far as refracting telescopes go, they haven't really caught on too much, certainly in more recent times in the professional community, because there are really quite severe limitations with them. This is the biggest one around, the Keyes 40-inch refractor, and here's a sort of more modern view. And the problem with this is, well, there's several problems. One is you've got a huge, great lens right at the far end here. And by the time you're getting to 40 inches, you're starting to get into sort of tons of glass. So you've got to support this huge lump of glass at the wrong end of the telescope, dangling up in the air there. So that's not easy. Glass is also hard to make pure enough that you don't block a lot of light, especially when you're going for lenses that are this wide and so consequently this thick. So making it optically pure and not losing a lot of light is one of the issues with that. So they haven't really found a lot of favor with professional telescopes. Much more common is the reflecting telescope, which I'm sure you all know about. So this is using mirrors rather than lenses, although this one does have a lens in the eyepiece. But you don't actually have to have a lens. You can just bring it all to prime focus and photograph it from there. Famously, Sir Isaac Newton had one of these, modest little instrument there. And they got to very large sizes in the 1900s. This is the Mount Wilson 200-inch reflecting telescope. And you can see quite how big that is, because here's a person sort of standing next to it. So that's a huge amount of mirror to point anywhere. And it does let us get on with the business of sorting out what's in the night sky. The other huge influence in the last sort of 20 or 30 years is the addition of CCDs. So, we used to work with photographic plates, and this is an image taken of the M42 Nebula by David Malin using, here is a 3.9 meter telescope, so a pretty huge telescope even today. And here's one I got Paul Money to send me. He taken with what's this, 180 millimeter telescope. And okay, David Malin's probably captured a little bit more there, but this is kind of, and I've seen much better images than Paul's, without wishing to say anything about Paul, but that isn't really the character of the telescope. It's much more about what's capturing it, the CCDs. So we usually talk about quantum efficiency with CCDs, or photographic plates for that matter, and that's really just a measure of, if you've got so many particles of light raining down through your telescope, how many can you capture in the CCD? So over here we've got photographic plate. They are anywhere between 1 and perhaps at their best 4 or 5% efficient. So 95% of the photons that come down from the night sky into the telescope are not caught. They end up somewhere else, and they're not caught on the image. When we get to CCDs, some of the top ones are now getting to 80 or 90%. So only 10% of the light is actually not doing anything, not contributing to the image. So that makes a huge difference. And they've got lots of other benefits too. So nobody uses anything but CCDs or the CMOS equivalent these days. So this comes back to the question, why are they so big? Why do we want this aperture fever? Why do we always want bigger and better things? And if you ask the average person in the street, they would say, well, it makes things bigger, doesn't it? You get much better magnification. And that's not really the answer, because I think we've all seen, every telescope has a sort of a kind of best magnification. And if you try and push it beyond that, it doesn't always get better. So some pictures of Jupiter that are sort of blown up a bit, and you can see by the time you've magnified it beyond the ability of the telescope, basically, you've almost got a worse image than the unmagnified one. So it's not about magnification, but there are two other aspects to telescopes that are quite useful. One is just the light gathering. So if you're trying to make an image and you want a nice image of it, you want to see all the details, then you need to catch enough light from it. And if you double the diameter or the radius of the telescope, because they're usually circular, you go up by the square of the capturing area. So here's a 5 centimeter one, which is 75 square centimeters of area, and this is a 10 centimeter, you're at 300 square centimeters. So you're already capturing a lot more light, and you can do more with it. But the big win really is the resolving power. And this is, I think, the only bit of maths in there. So, but stick with it if you don't like maths. It's a very nice and simple equation. So this is actually what a single point of light would look like if you could capture it perfectly. This is done by a laser, just for an example. So you see the pinpoint of light in the middle, which is actually the main bit of the light, but then you see all these fringes, these circular patterns that come out from it. And this happens with every telescope and even with your eye and everything. This is just a sort of blurring effect that you can work out the most central part of it, but then you get this sort of blurring around it. These are called airy discs or airy fringes. And it's governed by this rather simple formula. So this bit here, sine theta, which you don't need to understand or worry about too much, but this is how big this blob gets, basically. So that's a measure of how big it is. The bigger it is, the worse your image looks, because all the images collide with each other. And that's really only dependent on two things. One is the type of light, which is represented here by lambda. We seem to use lambda for wavelength of light in physics. So that doesn't really vary very much if you're in the optical. Red light and blue light are much the same. So you can actually effectively discard the top of the equation and say, well, that's just always the same. So the only thing that actually affects it is this D on the bottom, big D, because it's the diameter of your aperture. So this is how big your mirror is. And because it's on the bottom of the equation, the bigger this gets, the smaller this gets. So big D's make small thetas, which make small dots or small points of light. So the bigger you can get this thing here, the smaller that goes. So that's why we like the large aperture. The larger the aperture, the smaller this point of light. And that's pretty constant across all optical telescopes. Where you have to be careful is when this thing comes back into the equation, when this lambda term comes in. So, if it's optical light, it's all much the same. You don't have to worry about it. But if you go to radio waves or X-rays, you do have to worry about it because it starts to make a big difference. But we'll come back to that when we get to some new telescopes. So yes, size of aperture, that's important. And this sort of shows you what's happening. If you've got good resolution, you can see these two things here. They could be two stars, and you can make them see they're clearly separated. But as they get closer, the pattern overlaps, and eventually it just blurs into one. If you could get a bigger diameter, you could then resolve this back to these two points and make a much nicer image. And so you just get to see much more detail in the image. It isn't the whole story though, because otherwise we'd just be making bigger and bigger telescopes, but eventually you come up against other limitations, and one of those is the seeing. We always talk about seeing in astronomy, both amateur and professional, and that's just really about the quality of the atmosphere. If the atmosphere is waving around too much, or is kind of sort of what's called lumpy, you get little cells of atmosphere. Some of it slightly hotter than others, some of it slightly colder, and these all act like mini lenses, and they bend the light around slowly in different parts of it. But if you get enough of this, then you get a rather blurred image, because you get all bits of the atmosphere bending the light in slightly different ways, and they just smudge things out. So here's Zeta Bootes, which is a double star, but you can see sort of the main part of it here, but it's all spread out by this seeing. So, if it was a perfect place, such as on the moon, for instance, with no atmosphere, then there really are no holes barred. You can build as big a telescope as you can afford. If we come back to capturing light, though, this is the other thing we do a lot of with professional telescopes, is taking spectra. I don't know quite what the ratio is, but I wouldn't be surprised if it was 50-50. 50 we're making images, 50% for the time you're making spectra. That you're taking the light from stars and you're splitting it up into the colors of the spectrum, or beyond, in fact. So when you do that, if you've got so many photons of light coming through here, and you could put it through a prism, but we usually put it through a diffraction grating or a prism or something like that these days. So if you've got a certain amount of light from a distant star coming through here, and then you're spreading it out, each one of these, the bit in the red and the bit in the blue is going to be dimmed down by the amount you're spreading it out. So that's why capturing lots and lots of light is really good for spectra, because you're already smearing the amount of light out across a larger area to look at the different bits of the spectrum. So you really do need as much light as you can get. The spectrum looks something like this, but they're not usually colored because nobody wastes sort of a color imaging on that. They look much more like the next one, which is just a black and white trace with brighter bits in here and there where the spectrums are. So that's basically all the theory out of the way. You don't need any more theory really at this point. So let's go and have a look at some telescopes and see what we're using for research purposes these days. So the current state of the art, what we're using today and onwards. So I thought I'd start with this one. This one has been doing sterling work since the 1990s, I think at least. This is at Apache Point in the USA. I've just temporarily forgot. I think it's New Mexico. I ought to remember that. Anyway, it's called the SDSS for Sloan Digital Sky Survey. And this isn't a telescope that you typically sort of pick up and point at something in specifically. You don't say, oh, I'd like to go and get a bit more data on this thing over there. That's not how this one works. This one is a survey telescope, so it maps part of the sky. So it's like making a map of the sky, much like you make maps of the country. Instead of going to one place and turning up at the church and looking at that church and say, oh, what a lovely church. Instead, they're making a map of the city that it's in. And if you're interested in churches, then stretching this analogy quite far at this point, then the survey may well cover several churches within that area. So you can do something like that. But if instead you're interested in pubs, you'll also find that it's found a number of pubs as well. So this is kind of what this thing is doing. It's going across certain areas of the sky, making detailed maps of that sky at quite high resolution. And in fact, it got a recent upgrade and is now called, well, it's still called the same thing, but this survey it's doing now is called MANGA, capital letters apart from the A. I can't remember what it stands for, something. Apache Point, I think, is the last bit. And I think the G is galaxies, but all the acronyms in astronomy are very abstruse by now because we've used all the good ones. So this has a 2.5 meter mirror and a seeing resolution of about 0.05 arc seconds. So reasonably good. But as I say, nobody actually uses it to go looking at particular objects. It's much more for mapping. And then they produce large catalogues of all the things they've looked at. And then we dump them on our PhD students and say, right, do you want to study galaxies? Well, here's 500 that they got last night. Or I think they're up to over 1 million galaxies now. Similarly, they've done star catalogues and so on. So that's kind of where they're working. And in fact, this is kind of what they use for some of the MANGA stuff. So this was at a National Astronomy meeting, which I think is in Bath this year. But anyway, this is one of the plates they put over the telescope. So these holes here are sort of what fasten it to the telescope, and these little holes here with the circles around them, and my hand for scale, they are positioned so that when it points to a particular point in the sky, the light from, I think in this case it was galaxies, will drop through each one of these holes that were drilled very precisely in this disk. And on the reverse side of it, there'll be a fiber optic cable that will take the light just from that galaxy and take it off to be spectrally analyzed or to be imaged, whatever they happen to be doing that night. And then when, I think it takes about an hour or something to get one of these images, and then they'll unscrew it off, put on a new plate, go to a new position in the sky and take something else. So you can take sort of images or spectra of maybe 300, 400 galaxies in one go with this sort of setup. And that's what they kind of do most of the time. Very successfully too, they have. This is a different concept. So this is the large binocular telescope. And in this case, they've sort of changed things up a bit, and they've made it into effectively a large pair of binoculars. They're two 8-meter mirrors, which you can see there, and they work together. So they're working as a pair, much like binoculars. And that gives you some benefits. It also gives you a few headaches because you can see there it's two 8x4 meter mirrors. So you've actually got sort of the equivalent 11.8 meters or something in one direction and 22 meters effectively in the other, just for the way it's positioned. But that does mean that if you're looking at something, you're getting better resolution in one direction, say the horizontal direction, than you are in the vertical. So you have to take that into account when you're looking at things, that it isn't quite as straightforward as just putting your eyes to a pair of binoculars. And this is the inside of it, looking very shiny. And they've done some very good work. This is a picture of Io taken, so one of the moons of Jupiter, and I think they're working the infrared here. They're looking at lava spots or hot spots on Io. So that was one of the successful things they've done for that. So yeah, an 8-meter type telescopes. They're kind of state of the art almost at the moment. This is the one that people at our institution probably get to use the most, or it's certainly get a reasonable amount of time on. So this is the ESO, European Southern Observatory. So ESO is a collaboration of countries that all pitch some money in, and then they build telescopes, and the members can use them. So as the UK is a member of ESO, they obviously paid some money in, and we get to use them. So the VLT, or Very Large Telescope, is not really just one telescope. It's actually 4 telescopes, all pretty much the same design, all with the same size mirror, all done to the same spec basically, but they do all have slightly different instruments on them. So they have different types of spectroscope, different imaging, and so on. And so they each have their own sort of speciality. And in fact, yes, the number 4 one there has been fitted with laser, which is particularly useful for up and coming new technologies. It's also very useful for this particular telescope, because this lets you get rid of some of this atmospheric seeing. So I said before, the seeing, which is the sort of wobbliness of the atmosphere, making the image sort of wobble around very slightly, no matter what you do. So the science behind this is, if it's a bit like having a guide star. If you know there is something up there that should be rock solid, but it is moving around, then if you can get a computer to say, this thing that's moving around, I see what you're doing, I see you moving to the left and then to the right and up and down. If it's quick enough, it can bend a mirror that is in the sort of imaging train at exactly the right rate to counteract this. So although this image is jumping around, you get the mirror to jump around in the opposite way and take out all that wobbliness. So you can get very good resolution. You can push up the resolution even when the atmosphere is not as good as it could be. So you can see there we've got 4 8.2 meter mirrors, a resolving power of about 0.17 arc seconds, but they also have a trick where they all 4 can work together, and there are sort of tunnels underneath them where there's light guides and so on, so they can actually bring all 4 mirrors together as one underneath, and in which case you get very good resolving power up to this 0008, which I suspect is always going to be seeing limited, because only one of them has this adaptive optics. But these adaptive optics that take out the shimmer do help so here's a little animation showing the adaptive optics, looking at, I think, somewhere near this, yes, looking at the galactic center. So you can see that's with adaptive optics on, that's with just the normal smearing of the atmosphere. So if you can do it, it works phenomenally well and sharpens up your image extremely well. I think you can now even get such things, not quite as powerful as this, but you can get them for amateur telescopes now. So this is a picture of Betelgeuse taken with the 4 VLTs working in harmony. So you can actually see it's resolved to a disk, which is phenomenally hard to do with a telescope. Getting any star to resolve to a disk is pretty much impossible apart from the sun. But they managed it with Betelgeuse, which, to be fair, is particularly huge anyway. So if you're going to pick something, that's probably one of the easier ones. So yeah, the VLTs, they're certainly one of the cornerstones of our research at the moment. If you're going, unlike the Sloan Digital Sky Survey, which just does mapping all day, every day, these you ask for time on and you go after particular targets. So you say, I'm interested in Betelgeuse and I'd like to use all 4 telescopes. And in which case, it has to be a pretty convincing science case that you're going to do something new to tie up all 4 telescopes for a night's viewing. These are a couple of the biggest telescopes currently on Earth. They're not quite the biggest. There is one that's very slightly bigger, but these are the twin Keck telescopes. These are on top of Hawaii. So the VLTs are on top of a mountain desert in Chile, and these are on the top of a sort of volcanic mountain in Hawaii. Both of them picked because they're very high up. So already you've got rid of a lot of the atmospheric problems because you're already above quite a lot of the atmosphere. So that really helps with your seeing. It also helps with the weather because you're above a lot of the clouds as well. So you still do get a few clouds up there and you do get things like snow and whatever, but you're above quite a lot of the weather. So you get a lot more clear nights at that sort of height. And they're also picked because they're sort of in a reasonably unturbulent position. You know, the wind has just come across the sea. It hasn't come across mountains and valleys and things like that and got shaken up. So by the time it crosses here, it's fairly smooth, so you don't get too much turbulence. But these Kecks, they took a different turn when they wanted to make the optics. They decided not to go for a huge mirror. Both of these are 10-meter class telescopes, but they haven't gone for a 10-meter mirror. They've gone for lots of little mirrors that are stuck together. So that's kind of what a lot of people are doing these days. So these are hexagonal mirrors. I think they're somewhere around a meter or so each, something like that. You can probably work it out from that. But that is kind of how much of the bigger telescopes are going now. There's lots of advantages for going this way. It is a little harder to get them all aligned so that you make a nice, perfect sort of parabolic receiving area to get your images, but the sort of benefits outweigh that quite a lot. Firstly, it's a lot easier to transport you know, a meter-sized mirror than it is an 8-meter mirror. 8-meter mirrors, that you know, you find there are bridges you can't go under, there are roads that you can't trundle along because they're not wide enough to take an 8-meter mirror. So these are much easier to assemble in the first place. They're also much better for maintenance because with the VLTs, once the silvering in the mirror starts to deteriorate, they have to remove the whole mirror, sort of wash it down, remove all the silvering, put the new silvering on, let it dry, polish it up and whatever, and then return it. And I think that takes sort of the order of 1 or 2 months to complete, during which time the telescope is effectively useless. I mean, I expect they do other maintenance and stuff on it at that point. But with this sort of technology, you can just take one of the mirror panels out, wax it down or whatever you do with it, clean it up and put it back in, and then take another one out. And the telescope can still be used while all that's going on. So that is one of the big advantages for that. So that's kind of the state of the art really with optical telescopes on the ground, at least. What are we doing in other wave bands? So this is a fantastic sub-millimeter kind of radio telescope called ALMA, for Atacama Large Millimeter Array. So I think there's 66 of these dishes of various sizes, 12-meter and 7-meter. But they all work as one, so they all work as though they're one thing. They all point at the same thing, and the signal is all brought together and analysed in one go. And they can actually be moved around. So they have a little sort of a tractor type thing that goes around and picks these up and moves them around. So sometimes you want them all very close together because you want a very fine signal, or sometimes you want the biggest diameter, this big D by moving them as far apart as you can, still within the length of cable or whatever that's connecting them. So you can have these different types of orientation of these things. And it's really high up. You need oxygen and you need doctor's certificates and whatever to go up to here to actually be on site. And vehicles don't work particularly well at this height either because there's not so much oxygen around. But most of the, I think most of the control and processing is done much lower down the mountain because you only need sort of engineers here every so often just to go and hit them with a hammer or whatever engineers do. So when they're working together, they're extremely effective, 5 times the resolution of Hubble at their best. And this is one of the stunning images they've taken. This is of this is in the infrared, so there'll be a star at the center of this, and this is a protoplasmic dust cloud surrounding the star. And these grooves here, we believe, are cut out by planets that are forming around this star. So when this first appeared at conferences, which was about 3 or 4 years ago, everybody was just knocked out that we got this sort of level of detail of nearby stars and the process of planetary formation. So that is one of the stars of today. You know, if you can get time on ALMA, you're doing very well. Going to much longer wavelengths, Jodrell Bank. I'm sure some people have been there. I'm sure Wendy must have been to Jodrell Bank. So this is a 76-meter dish, but because you're now working with very long wavelengths down in the radio, the resolution is not terribly good. Even at 76 meters, you're only getting about 1 degree of resolution. So you can only see the biggest things you can resolve are 1 degree across. So although that's great for the things some of the things they want to look at, they often want to do much better than that. So they hook together several of these telescopes. And this is when it's working this so-called very long baseline interferometry. So when you're working with telescopes across the world, certainly across Europe or across the UK, depending on who's joining in at the time, then this would give you much better resolution. So you can see there, with this very long, depending on how good your contacts go to other radio telescopes, you can get down to 0.001 of an arc second, but you need them widely separated. And of course, this came to its sort of logical conclusion with the picture of the black hole about 2 years ago, where they took this to extremes. A big radio telescope that's sadly no longer working is Arecibo. So these are the fixed dish idea that whereas Jodrell Bank you could steer and point at different areas of the sky, this one really can only look overhead, although it can't look anywhere now because it's fallen down. But it was one of the biggest radio telescopes, but it's now been exceeded by this one, the FAST 500-meter Aperture Spherical Telescope, built in China, to a similar sort of design, but much bigger in scale. So this is 0.5 kilometer across, this from side to side, so really big. And kind of looks like this when you see it. It's now up and working. Although the acronym FAST, 500-meter Aperture Spherical Telescope, is sort of wrong in nearly every way possible. So although it's 500 meters across, they actually only use 300 meters at a time because they use different parts of the dish depending on where they're looking. So if you're looking straight up, you're using sort of the bowl of the dish. But if you want to look slightly to the side, then you use different areas of it. It's also not spherical. I think it's parabolic. So you know, they went with the acronym first and they filled in the gaps afterwards. So just for comparison, so here's the Lovell telescope, Jodrell Bank, at 76 meters, and the biggest steerable dish at 100 meters. This is what Arecibo looked like, and this is what FAST looks like. So you know, bigger is better in this case. So that's sort of a quick run through some of the bigger telescopes on Earth. The next thing we go to is space telescopes. Now, why do we want to go to space? There's good argument. This is something we always test our undergraduates on one of our courses, where they have to give a little presentation on telescopes. And they all seem to gravitate to space telescopes, and we say, well, what are the pros and cons of it? Well, the pros are you get much better big pictures in space, and the cons are it's about 10 times more expensive to do anything in space than it is on the ground. And also, if it stops working in space, you're done for. On the ground, you can send out an engineer and fix things. But in some cases, we don't have much choice. So this is another Wikipedia image, and this shows what makes it down to the ground from out in space at different wavelengths. So this is the visible spectrum. You can see that gets down to the ground, providing there's no clouds about. This is into the infrared. So there's various gaps in the infrared, but there are some places you can't see through particularly well in the infrared, these sort of spiky bits. They're usually molecules like carbon dioxide or water or something like that that soak up the infrared, so you can't see those. If you go into the far infrared, it's completely blocked. You can't see anything in the far infrared from the ground. The atmosphere blocks it completely. There's a big hole here for radio, so that's why radio is very popular. You can see out there, unless you go to very long wavelengths, when again the atmosphere acts more like a mirror, and so the long wavelengths sort of bounce off the atmosphere and back into space and never make it through. Going in the other direction, so ultraviolet, a bit of that comes through. That's kind of what gives us the sunburn, but only bits of it. Some of the more juicy ultraviolet is blocked by the atmosphere. And then up to X-rays and gamma rays, they're all blocked by the atmosphere. So if you want to go observing in those, and there are some interesting things you can look at in these wavelengths that you can't see from the ground, then your only option is to go to space. You can't, it's not an either or. You have to go to space or not do it. So what have we done in space? Obviously, we've got to start with the Hubble Space Telescope at 2.4 meters. Not a great resolution at 0.05 arc seconds, but it's always pretty much uninterrupted. You don't get clouds in space, you don't get light pollution, you don't get the atmospheric shimmer. So it's always pretty much as good as it gets at that wavelength. It's coming to the end of its life now. We're hoping it lasts another year or two at least, but it hasn't been, it was fixed by sort of 4.5 missions in the space shuttle, went up and changed things out a bit. But I think the last one was about 2012, so it's kind of 10-year-old parts now, and some bits haven't been changed since it was launched in 1990. So getting quite old. And if you think of what technology was like in 1990s, if you think what your mobile phone was like in 1990, if you had one, and what it's like today, you can see we made big advances in that time, and you'll probably do things differently if you're going to do them again. But anyway, Hubble is still doing excellent work and is still very difficult to get time on if you want to apply for time on the Hubble. I think it's about 10 to 1. So for every 10 proposals astronomers put in for time on the Hubble, 1 gets accepted and 9 get rejected. So you've got to be made of tough stuff to apply for time on Hubble, because you're going to be crying a lot of the time. So classic image from the Hubble. What else can we do in space? We can do X-rays. So the X-rays are blocked by the atmosphere. So we've got 2 that are working at the moment, XMM Newton and Chandra, both sort of reasonably similar in their scopes. So they each have their own quirks and abilities to do things, but they will both take X-ray pictures, and they're getting better all the time. So this was an earlier one. This was called ROSAT. This was the predecessor to both of those, and this had a 30 arc second resolution. So this is looking at the Crab Nebula pulsar at the very center of the Crab Nebula, and you can see there's a bright something here, and there's some sort of structure going on there. Not really too sure what's going on, but clearly something is. When we get to XMM Newton or Chandra, then suddenly this leaps into much better focus, and you can see now there's a sort of a spiral structure going on. This thing looks like a jet coming out here, So suddenly from the very fuzzy picture we got from ROSAT, we're getting a much better image from the more modern telescopes. And this is quite a breakthrough in some ways, because certainly when I first studied physics, which was quite a few years ago now, you couldn't focus X-rays. X-rays were just things you could block. So you could lie on a bit of photographic film and have X-rays shone through you, and your bones would block some of it, and you could see your skeleton with them. But you couldn't take a picture with X-rays. But since those days, we've learned a little bit more about them, and now it is possible to focus X-rays to a certain degree. And this works like this. So this is a picture of a mirror, but these are the individual atoms here that make up the mirror. And when you get something like light coming in, light is a much bigger wavelength than the space between atoms. So light tends to see the surface of the mirror as just a flat thing, and it comes in and bounces off it if it's nicely polished. So light doesn't really see the cracks. It's like walking across a cattle grid or something. You don't fall through the gaps because your feet are big enough to step across them. But with X-rays, they are very tiny in wavelength, so they will easily fit between the gaps. So that's kind of why they don't focus or do anything, because they just fall between the atoms and get lost and rattled around. But there is a trick you can play, which you can also play if you're out and about near a lake. So if you come in at a very, very fine angle, then from the X-rays point of view, the surface doesn't look like a grid anymore, because you're looking at a very fine angle. It looks very flat. So the X-rays just sort of bounce off. And this is very much like skimming stones across a lake. If you just throw the stone into the lake, there's a plop and it just disappears and you'll never see it again. But if you spin it and skim it at a very fine angle, you can get it to bounce off the lake. And sometimes I manage to get 6 or 7 skims. I'm sure people have done better than that. But that's basically how the X-ray telescopes work. So what they are sort of concentric rings of some sort of glassy material, sometimes glass or sometimes coated glass. And the X-rays come in at this very, very fine angle of about 1 degree to the surface. And they sort of skim across the surface and are slowly focused up to, well, they're moving at the speed of light, but they're focused very small angles to the center to make an image. It only works with soft X-rays. So X-rays of reasonably long wavelengths. When you get to the hard X-rays, the ones that are verging onto gamma rays, then again they would just find their way through the cracks in the mirror. But this is something that's made X-ray telescopes much more practical in the time since I was originally studying physics. If you want to go all the way up to gamma ray telescopes, these are even tinier wavelengths and much more lethal. So this comes from atomic transitions, or nuclear transitions actually. In that case, then you really don't have any option. You have to go back to the sort of X-ray original thing where you make this sort of shadow mask, and the gamma rays come in and they sort of fall through this shadow and they make a pattern on your detector. And if you get a very clever coded mask there, you can actually take it from several angles at once, because you get a different sort of pattern depending on which way they're coming from. So there's some clever stuff that goes into that. And you also have to slow the gamma rays down and turn them into electrical signals, which is kind of what that does. But if you take pictures across the galaxy, so this is out into space, this is the galaxy across here, the Milky Way, and this is below and above it. You can see there's these big bubbles in gamma rays that we weren't even aware they were there, called Fermi bubbles now. So the stuff we're discovering by looking in different wavelengths. Now, if you go the opposite direction, so you can look some of the infrared, there are sort of gaps that you can look through the atmosphere with infrared telescopes, but it's much better going into space, because you're not restricted to just looking through these tiny little gaps. You can get the whole picture. So Spitzer, I think Spitzer's stopped working now. I'm not sure. It was working for a long time in its full capacity, and then it stopped working at its full capacity and went to limited capacity. I'm not sure if it's finished with that. So the issue with infrared telescopes is infrared is given off by anything warm. And if you're not careful, the telescope itself will be warm. So you end up taking a picture of the inside of the telescope rather than what you're pointing it at. So you really need to cool the telescope down to a considerable degree. So these are nearly always launched with lots of cooling fluid like liquid nitrogen, liquid helium or something like that to keep the telescope very, very cold so that it doesn't mess up the infrared signal and you don't take pictures of the internals of the telescope rather than the stars or galaxies you're looking at. So that's what kind of limits the life of these telescopes, that eventually this liquid nitrogen, liquid helium heats up, boils off, and you no longer have the cooling technology left. But that lets you take images like this. So this is looking at a galaxy in infrared, and it's picking up the dust, the glowing dust lanes all around it, which glow particularly in infrared. So you can't particularly see the stars in this image, but you can see where all the dust is. So if you want the whole picture of what's in a galaxy or what's in a star or whatever else, doing this sort of multi-messenger or multi-wavelength thing really gives you a much better picture. And although astronomers used to see themselves as radio astronomers or visual astronomers or X-ray astronomers, these days they're much more across all the wavelengths. So they might well take optical, but they would take infrared and X-rays if they were useful to look at whatever it is. The far infrared, there's only been one really major mission for that. That's Herschel, which is still, as of now, the biggest mirror that's ever flown at 3.5 meters. But now you're into the far infrared, so much, much longer wavelengths, and that lambda at the top of the equation is starting to hurt you now. So even though it's a big mirror, it's not particularly good resolution. But it opened up this far infrared that we can't see from the ground at all. And suddenly we had the sort of whole picture. We could see what was happening across these hidden wave bands between the radio and the nearer infrared that you can see from the ground. So that did sterling work, but that had to be cooled very severely. And that ran out of coolant several years ago and has now gone off into a solar orbit, I think, to make room for other telescopes. Couldn't leave it without saying something about Kepler, which has made probably the biggest haul of exoplanets so far, planets around other stars. So just staring at this little area next to Cygnus, which is now coming into view, it's detected, I think, somewhere around 2,000 confirmed exoplanets and another 2,000 or 3,000 that are quite possible that we'll eventually get up to following up and proving one way or the other. So very good mission, very successful, but has run out of steam now and been retired, being replaced by other missions. Gaia, also coming to the end of its time now. This is a mapping mission for the Milky Way. So it's working out positions, locations, and movement of the nearest billion stars in the Milky Way. So we're getting very good imaging of stars in the Milky Way, giving us a sort of GPS for the Milky Way. So this is where we are. You get very good resolution of the stars in this area, and even out to this area, we're getting some good measurements. So not only exactly where they are, but also how they're moving, their proper motions. So that's kind of where we are today, but we've got stuff to look forward to. So the third part of the talk is what's coming up, what's to come. And I've got to start with this one because we have a certain amount of involvement with this at Nottingham. We're not building it or anything like that, but our professor sits on one of the panels that reviews instruments that are going into this. So this is the ELT, or as it used to be known, the ELT, because it's the European Extremely Large Telescope, and it's a gigantic monster. So I said the biggest telescopes in the optical at the moment are the Keck telescopes, or there's also one on Canary Islands, about 10 meters or 10.5 meters. That's the sort of range. So this is 39 meters. That is huge. I mean, it's just vast. It's a massive piece of engineering. The companies that are bidding to build this sort of structure here, they usually build football stadia because they're that sort of level of building. And you can see how big they are compared to a person, a truck, Arctic lorry, and so on. So it's about half a football pitch of collecting area that has to be positioned optically perfectly, no matter where it's pointing. So, you know, it's going to be one of the wonders of the modern era. Here's what the mirror looks like when laid out. This isn't the mirror, the real mirror. This is a cardboard cutout, but this is how big the mirror is. You can see it's absolutely huge. Compare it to some other big constructions. Okay, it's not quite as big as the pyramids. It's much bigger than the VLTs, which are sitting here. They don't normally sit there. It's comparable to Big Ben. You've been there. It has 5 mirrors in it, so it has this huge primary mirror, and then it sort of bounces up to a secondary, to a tertiary, to a fourth, and then to a fifth that sends it out to the instrument. And I think it's this fourth one that we'll be using with adaptive optics. Just to see how big it is, here is this is one of the Naismith platforms where the light will appear from, and somebody here in the CAD drawing has put one of the VLTs just sitting on this platform, so you could have one of the VLTs as an instrument, the ELT effectively. It won't be much good without adaptive optics, because at 39 meters you're not diffraction limited, you're limited by the seeing. And because it's taking such a big path through the atmosphere, this 39 meters, it doesn't need just one laser, it needs 4 lasers to work out what's happening in all these parts of the atmosphere. And to bring all that stuff together needs a very sophisticated computer and quite a lot of clever work to bring all that together. And just some of the specs, just for fun: 798 of these hexagonal mirrors, which is 259 tons of mirror. You know, even the secondary is a 4-meter mirror, and a 2,800 ton main structure. So pretty huge, and going to be the biggest optical telescope for a while to come, I suspect. But it's not the only game in town. There are a couple of others that are not quite as big, but are under construction. So there's this one here, the TMT, the 30-meter telescope. I usually get people to guess this, but it doesn't work so well in Zoom. So TMT, 30-meter, and as its name implies, it's 30 meters across. 2022 is not going to happen. That was ambitious marketing on their part, particularly with COVID and everything else. But even worse than that, this was trying to be built in Hawaii at the top of the mountain, and that has got mired in lots of legal challenges by the Hawaiians, who don't want any more telescopes on their mountain. So it's gone through all sorts of legal issues. It's been given the go-ahead, and then there's been another court order that stopped it, and people have campaigned against it and blocked the roads. And also, I think last I heard, it's probably still going ahead, but everything's shut down for a while. But anyway, if that does go ahead, it will be much on the same plan as the ELT and the KEX. It'd be hexagonal mirrors all slotted together to make something big. And the other really big telescope being built is the GMT, the Grand Magellan Telescope. But this one, they've gone back to sort of old technology. They've gone back to these 8-meter mirrors, but this time they've got 7 of them. So there's a central mirror here, and then 6 of them around it. So it's kind of like the large binocular telescope on steroids, that they have just sort of packed it out with extra mirrors all around it. And I think most of those mirrors have now been cast and built. In fact, they've also built an extra one of these outer ones, so they can take one off, put on the spare one while they resilver it, so they don't get too much outage. Here's one of the mirrors being cast in Arizona, under the football stadium is where the mirror lab is, and that's where they make their mirrors. So all the glass is positioned here, and then it's covered up, heated up to whatever the melting point of glass is, 1100 degrees centigrade, something like that, and then cooled down very, very slowly over months to, and I think they spin it as well to sort of even things out. And then hope nothing cracks. And then they go into a sort of months of polishing then to polish the mirror. So much like you'd make any mirror. And here's an artist's conception of it. This will also be in Chile. So rather than fight the politics on Hawaii, they've gone back to Chile, where Chilean government are quite happy to welcome telescopes and the money that comes with them. Another one, this one is almost finished now. So it was called the LSST and has been renamed Vera Rubin Telescope in about the last year. So this is a bit like the first one I showed you, the SDSS. So this is a large synoptic survey telescope. So this is another survey telescope, not one you go and point it to anything of interest. This is a mapping telescope, but it's kind of mapping on steroids at this point. It has a huge camera attached to it, and not a huge mirror particularly. It's only an 8-meter mirror, but it has this huge camera. So here's a lady holding up the camera, and this would be an image of the moon on that CCD. So yeah, it's a 3.2 gigapixel camera. So it's taking vast quantities of data on every image it takes. And its mission would be to take a 15-second exposure of somewhere in the night sky, slew a bit to the side, take another 15 seconds. Well, it takes 20 seconds to do the slewing, and then another 15 seconds, and just chunk around the sky all night. And I think it covers the entire visible sky from where it sits, which I think is in the USA, or actually I'm not entirely sure. It could be back in Chile. But anyway, they reckon they should be able to cover the entire night sky every 3 days, basically. So then you can compare, what was happening 3 days with what was happening today. And that lets you pick out transient objects like supernovas, exploding stars, also asteroids, minor planets that are moving. They would differ between these two things. And the amount of data you're going to get from this telescope is just phenomenal. It's going to be terabytes a night coming from here. So much so that people are really quite worried about how you're going to be able to process it quick enough, how you're going to be able to do enough with it. So it's got beyond the ability just to throw PhD students at it. We've got to throw machine learning computers at this amount of data. Next big thing in radio telescope is called the Square Kilometre Array. So this is a big array of telescopes spread across 2 continents. And again, you're down into the radio. So this D, the bigger the better. But now you've got a long wavelength. So these 2 things are fighting against each other. So this is where these are going to live. So quite a lot in South Africa and Western Australia. So originally they wanted to either go in one place or the other, because it's just much easier to manage the telescope if it's in one country, for goodness sake. But politics came down. Both Australia and South Africa put in good bids, and politicians did what politicians do and said, well, you can have half each, basically. Though it's a little better than that. The Australian are going to be working at slightly different wavelength to the South African. So this is Square Kilometre Array. This is going to be all these dishes all linked together with a fibered cable. And the idea being that if you add up the area of all the dishes, it's effectively 1 square kilometre that you're observing with. And you can see a few telescopes here on outposts on Madagascar and across Africa. So you get some of the long baseline that gets you a better resolution. And you can also work with some of the stuff in Australia. So very good stuff. What's happening in space? You probably all know about this one, the James Webb Space Telescope. This is a mock-up of it on the ground. So it is pretty big. It's a 6.5-meter mirror. It's not quite a replacement for Hubble, because it sees mostly in the infrared, a little bit into the red end of the visible spectrum. But infrared is kind of where it needs to be, where astronomers really want to take images, because there's lots of advantages to this sort of size infrared. So yeah, astronomers are chomping at the bit, waiting to get to use this. Hopefully it will be launched this September, October time. This lovely animation, because this is what you actually have to post in your rocket, and it has to be unpacked on its way to its location. It's going to be parked at about 1.5 million kilometers from the Earth, so way beyond the moon, at the L2 point where lots of telescopes live. And it has to do this sequence of about 300 operations while it's getting there to be a fully functioning telescope. And there's no chance really of a rescue mission for this if it goes wrong. If it doesn't, all these things don't work, then you haven't got a working telescope. NASA have said that all these telescopes that are going to distant places should now be robot serviceable, whatever that means. There are no robots to go and service them, but I think the idea is you make the bolts big enough that a robot could undo the bolts and change bits out if it had to. So looking ahead, because this was conceived in the 1990s, very soon after Hubble was launched, originally destined to fly in about 2006 at the cost of somewhere between $500,000 and $1 million. $1 billion, sorry, $1 billion. Yeah. Here we are, 2021, still not launched, so it's late by anybody's scale. It's also now well over $8.5 billion being poured into it, which you know, it's for a while it's been too big to die. You know, we've spent so much money on it, but you've got to spend the extra in now to sort of get it finished and launched. And it's stolen a lot of money away from other projects. Other people wanted to do exoplanet missions and things like that, and most of the money was going into just finishing this off. It will be a fantastic instrument. People are already applying for time on it, putting proposals in. So, you know, providing it works, it will be fantastic. Another interesting one, this comes a bit later, this is in the mid-2020s, is the W1st, as it used to be called, and now called the Nancy Grace Roman Telescope. This is an interesting telescope. It was conceived before things sort of started with this, in that they had a plan for this telescope and what they wanted to do with it. And then the arm of the American government that runs spy satellites came along and said to them, we've got a couple of Hubble class telescopes that we're not going to launch anymore. Would either of them be any use to you? And they said, you've got what? Because nobody knew about them. So they said, yes, yeah, great. What's the cost? Well, they're free, but you just have to pick them up and take them away. So people were ferried off in sort of blackened limousines to secure facilities in the middle of nowhere, probably blindfolded and whatever else, and then they could inspect the telescope and say, yeah, this will be great. So they said, that's fine, we'll package it up and send it to you, ask no questions sort of thing. So anyway, this turned up and helped a lot with the funding of the proposal, because they now have the telescope. It wasn't everything they wanted in a telescope, but it was pretty close, and it was free, so I'm not going to turn your nose up at that. They did break bits of it on purpose, because it was originally for spy satellite technology, so they wanted to break, I think it was the third mirror or the secondary mirror, or one of the mirrors, so that they couldn't work out exactly how good the technology was they were using. But anyway, they've got this now, and this will be launched. It has a different mission profile to JWST and Hubble. And one of the things it would like to do is look at exoplanets. And there's another intriguing mission, which we've no idea whether we'll get funded or not, but is a possibility. So that's this thing here, this sort of flying feathery thing is a star shade. So this is a completely autonomous sort of spaceship, and you fly it around in between your telescope and a distant star, such that this thing sits in between the two and blocks the light from the star. And then you can look at where the star would have been, but most of the light from the star is blocked out, so you can perhaps see the planets that are going around it now that it's shielded from it. Whether this will ever fly, and if it does, whether it will actually work with these. So both the James Webb and the Nancy Grace Roman telescope are designed to work with this should it ever actually appear. I don't know whether it will, because it takes sort of like a month or two to move this star shade from one place to another, because you can see it's 30,000 kilometers away from the telescope. So, you know, the slewing time for this star shade is quite considerable. But anyway, I thought it was fun to throw in. In exoplanets, we've got Cheops and Plato. Now, one of these has launched, perhaps Cheops, and one has yet to come. And there is another mission aimed at exploring satellites. So one of them's looking at in more detail at known exoplanets, and the other one is which is Plato. I think that's looking for nearby stars and seeing if they can find planets around those. So Kepler had a very fixed point in the sky, whereas this one is going to look at all the nearby stars and look for very handy planets. In X-rays, we've got X-RISM from JAXA, the Japanese Space Agency, and the Athena ESA, European Space Agency X-ray telescopes. Both of them much better than the XMM Newton and Chandra that are around, so they will push the technology on. And then one final telescope that never got built, but would have been fun if it had. And this was the original ESO proposal for OWL, the overwhelmingly large telescope. So this is a 100-meter telescope. You know, that is outrageously big telescope. And it was, they hummed and hawed about it for a while and decided they thought they could probably build it. They might be able to build it. We could probably get it working. But in the end, they thought it was too big a risk. And so they backed down to the ELT and went just for 40 meters rather than 100 meters. But, you know, maybe one day this will be a reality, or perhaps next time around. So this is a very nice Wikipedia image that shows the relative size of the various telescopes. So here's the Hubble down here, the Kepler. Somewhere we've got the James Webb, which I can't see. Oh, there it is next to it. There's James Webb. So you can see it's quite a bit bigger than the Hubble. Got a standard tennis court and a basketball court for size. Here's the ELT. You can see how big that is. Here's the 30-meter and the giant Magellan. The 4 dishes of the VLT and the large binocular. The Gran Canaria, which is actually the biggest one at 10.5 meters, currently working. The 2 Kecs. And you can see this ghostly image in the background, this grey thing, that would have been the OWL. So you can see how big that OWL telescope would have been compared to, you know, you could comfortably fit all the existing mirrors inside that and still have room to spare. So yeah, oh, there's the Yerkes refractor up there. So, you know, tiny telescope, and the Mount Wilson 200. So yeah, that's a good image of telescopes. Just to finish up, a few what's to come into the far future. So given it took the James Webb from concept drawing board in 1990s to still not being launched in 2020, we've got to start thinking what's going to replace the James Webb if it's going to be sort of 20 years. So LUVOIR is certainly one of those. I don't think there's anything nailed down at this point, but this is one of those telescopes that might be coming along. Large ultraviolet optical infrared, so you know, covers all the bases. And this should be missed it. Let me go back and try that again. So this is much on the same scale as the James Webb. You know, it's an unfolding origami type telescope. A lot more sophisticated folding up, I suspect, to get this to all work out. But we'll have a huge mirror on it. I doubt it will actually appear in this form because there's a lot of hurdles to be jumped over between here and then. But you know, it'd be a fantastic size telescope, and would do some excellent science if it ever got there. But it might well combine with another telescope. You know, they might say, well, there's 2 or 3 of you all pitching for more or less the same thing. Why don't you join forces and come together? That's often what happens. Other mediums, we have neutrino telescopes now. They're not very effective. They capture a handful of neutrinos every day, so not good for seeing everything. Gravity wave telescopes, so these certainly come good in the last few years. LISA mission is scheduled for the 2030s, so that's taking it into space and covers a different wavelength effectively to LIGO, so that brings things in. Dark matter telescopes, that's my best picture of a dark matter telescope, because we don't know what that is. And finally, just to finish up, this is the Hubble Ultra Deep Field. If I just go back to that, get that to play. Yeah, so this is just to zoom in on that. So that's my last slide. And thank you all very much for listening. This is what the Hubble did, staring at a patch of sky continuously over, stacked together 11 days worth of imaging.
Excellent. Thank you very much, Julian.
Yes, thank you.
Yeah, it's a wonderful whirlwind. And I'm sure that's, I've lost count of the amount of telescopes you've taken us through. So I'm sure there's lots of questions. So
there's quite a few I missed out. So if I missed your favourite telescope, I apologise. It's long enough as it is.
Have? Yeah.
I'll stop sharing for a bit. So
I'll kick off then. With all the big new telescopes, I assume there's probably a limited budget if you added up all the scientific academies. Does that mean that we're going to lose some of the smaller ones, that they're just not going to be funded and we're just going to get fewer, bigger telescopes?
That's a really good point. Yeah, no, that's a very good point indeed. So I don't think they're really, some of them may go, some of the older telescopes may well go. In fact, which one is it? The 30-meter telescope, which was going on Hawaii, part of the deal to get that onto Hawaii, that was originally, they had to dismantle, I think, 3 telescopes or 4 telescopes to put that in there. So that was okay because some of them had sort of reached the end of their life. I don't think things like the VLTs will be going anywhere anytime soon. And the big problem really is there's probably like 10 or 12 8-meter class telescopes in the world at the moment. So if you want 8-meter class data, it's not that difficult to get time, providing you're persistent enough to, you can apply to the VLTs or the KEX or Grand Canary or whatever else. But there's quite a few you can go to and try and get time. When we're only going to have 2 or 3 really big telescopes, they can only be used for one thing at once. So the amount of time you'll get on any one of those is going to be very limited. Or actually what's going to be more the case is the proposal thinning is going to be much worse. So certainly with the ESA telescopes, it depends what consortium you're in, but if you're in ESA, anyone in ESA can bid for time on, say, the VLT, and it's just an open tender. You make a science case and you fill in an ESA form and say, ESA form, say, this is what I want to do, this is what the science goals are going to be, this is how I'm going to process the data, this is what I hope to find out. And then it goes off to a telescope allocation committee and they sift through them and they say, well, we have 360 nights a year. You have telescope proposals for 600 of those nights. So we're going to have to whittle them down and perhaps the top third will be selected. And there's all sorts of machinations that go on. It's usually driven by science, but you have to decide which ones will get funded and which ones won't. So there's a bunch of astronomers who sit around and go through all the proposals. So when that gets to something like the ELT, you're going to get even more proposals come in and less nights. So your chance of getting time on those is going to be even more restricted. So yeah, it's going to be an interesting time.
Yeah. I've heard a number of people talk about their PhDs and it's like linked to telescope time of what they're actually trying to do and discover. So does that bode well or poorly for future people going into astronomy and astrophysics?
It doesn't. It doesn't. We've actually got more data than we have PhD students to analyze it. So usually what happens is they get data from something like the Sloan Digital Sky Survey. So you might start a project saying, I want to compare red galaxies to blue galaxies or something like that. So I go to the Sloan and I download 1 million galaxies and say, here's the blue pile, here's the red pile. I start comparing them, start writing a paper, and then you find something particularly interesting about one of them. One of them stands out and says, well, this doesn't really fit in either camp. I wonder what's going on with that. We really need some telescope time on this particular object to follow that up and get to the bottom of it. And that's when you write your proposals. And this SAGE group sits around and decides whether your proposal is any good or not. So that's often how these things work, that you don't usually set off with your PhD thinking, right, I've got a bright, shiny telescope. What am I going to do with it? You've got to sort of make a case, usually by publishing other papers to show that you're not just going to fritter away the time you're given, that you're going to do something useful with it. So usually it's towards the end of your PhD that you get to do observing runs, if you do. And they're quite ruthless. They say, you want an 8-meter telescope? I think you can do this on a 4-meter telescope if you pushed it. So go off and use a 4-meter telescope. We've got things that really, really need the 8-meter class for this. So, it's swings and roundabouts. You have to argue your case strongly. No, I won't get the resolution of a 4-meter. I really need the 8-meter to really pin this down. Well, I don't know. Reject. Send it in next year and try again. And this time maybe it will be accepted. So yeah, a lot of shenanigans go on.
Yeah. Feel free to unmute yourself and ask a question if you've got one.
Oh, I see Wendy managed to resolve what MANGA stood for. Mapping nearby galaxies at Apache Point Observatory. There we are. I knew there was galaxies and Apache Point in it somewhere. Thank you, Wendy. Yeah, they're all very contrived by that time.
Have you been guilty yet, Julian, of contriving an acronym?
Not so far. No, I've been involved in projects that do have most of ours are a bit less crazy. So I was part of a project called the 300, which was based on the film The 300, the Spartan Greeks. Yes, so they had 300 simulations of clusters of galaxies. So, and they even had names for some of them, named after the famous Greek warriors of the 300, whatever. So, but they were just called the 300. So that was about as exciting as I got. So anybody want to go the Aperture Fever? What's the biggest aperture you've got in Bath, do you think?
I don't know, actually. What's your telescope, Charles? Is it 14? Oh, quite.
He's frozen.
He's frozen again, is he? He's probably not even here. I think they've got some 14s up at the university, but nothing big. And we've got quite a bit of light pollution. We're not as blessed as Roger in Sparkford with his beautiful Bortle 4 skies. Yeah. So another thing I was going to ask, when Starlink went up, Elon came back with a comment, why are you building your telescopes on Earth? You might as well put them better in space. Mm-hmm. Have you had an opinion on that, Julian?
Well, it's really expensive to put them in space. That's the problem. And if they go wrong, there's nothing much you can do. They're much better in space than on the ground if everything was equal, but everything is not equal. Putting them on the moon would be a brilliant place, I think, particularly on the far side, because you're shielded from radio waves, light waves, and all sorts of these things, and you have a nice solid thing, and I think you could have them manned for a reasonable amount of time. So if you put new instruments on them, so most of these telescopes are not kind of static. So the VLTs, they have a range of instruments, and they sort of move them around. So that I think there's about 3 or 4 instruments on each. So they sort of have 3 months with this instrument on it, and then they move that out and put a different instrument on, and then every year or few years they have a brand new shiny new instrument that they bring in. So you can't do that quite so easily in space. You might be able to do it on the moon, although I suspect it would still be pretty hard. But yeah, being able to bring in these new instruments, take advantage of new technologies, redo the CCDs with CMOS or something like that. All these things are possible, but much easier when somebody can just walk up to it and undo a few bolts and put in something new. But yeah, out in space, you do get the best pictures.
Yeah. I wonder what you do if you managed to convince Elon on all his Starlink satellites is to put cameras on the backs of every Starlink. So you'd have 40,000 cameras, not pointing down, but pointing up.
Pointing up. Wow, yeah. Yes, you might even be able to do some sort of long baseline interferometry type, although it's pretty hard to do with optical. It's much easier to do in radio with that sort of thing. But yeah, that would be fun. They could really do with ultraviolet cameras. We're lacking in ultraviolet imaging. So I think the Hubble can just about stretch into the ultraviolet, but there haven't been any sort of dedicated ultraviolet cameras for a while. So yeah, putting a few of those on Starlink would really help.
Can I have a go? If I'm not
Good, Charles. Yeah.
I've always been puzzled by the practicalities of adaptive optics. I mean, anyone who's used a visual telescope can just see how fast the scintillation is. And you have to have some means of having your laser pointing up in the sky. You need to be on the same light path, I presume, as the actual scope itself, and be confident about that without actually destroying the image in the process. And then you have to pass the information about the scintillation speed fast enough to actually get the mirrors to adapt in time. And it just seems implausible that can all happen fast enough to be useful.
Yeah, it is. It's not easy. It's much easier to do with infrared. So they've done a lot with infrared. You can do it with optical, but it as you said, the processing has to be pretty fast. So the atmosphere shimmers on about somewhere between 100 milliseconds and 10 milliseconds, somewhere in that sort of. That's the sort of speed you have to be going to process this. So if you can process it, perhaps twice that speed, then you can make a reasonable guess at what the atmosphere is going to do and sort of take it out. It is still, people are still working on it. They're still coming up with new algorithms on how to process it. They're usually helped by being in particularly stable parts of the Earth. So, high up mountains or deserts with very low moisture contents, things like that. They help make it less of a guessing game. But as you say, it's pretty hard to do. So
does that slow down the variation as well? So I can imagine if the air is very smooth and very, very clean, so to speak, does it mean the actual rate of change is less as well? Because of course, if it's varying less fast, it's easier to keep up with it.
Yeah, I think it's being predictable, I guess, is kind of what you want, so that your computer can make a prediction, say, well, this is what's going to happen in the next 10th of a second. This is what I'm going to do to counteract that.
Oh, it actually predicts. It doesn't just follow.
I think I don't know, actually, to be fair. I think there's some element of prediction, but
amazing.
Who knows?
Okay,
You'll have to speak to somebody who really knows.
Yeah, no, I understand that. It's a bit of an obscure aspect of it, but it's always puzzled me. Thank you.
Yeah. Well, it's not completely random, is it? It's because it's effectively waves. That turbulence. It's almost as if you see the turbulence coming in. The next sort of phase of it isn't going to be completely random. So you do get a sort of, there's a trend that you can correct for, but you won't be able to 100% correct it for it.
Yeah. I think that's sort of what I've heard, although I've not heard very much. So
thank you.
And there's people in Edinburgh who work on this sort of thing. Quite a lot of instrument people work up there on that sort of adaptive things. And yeah, as you say with the ELT, if you don't have adaptive optics, then this huge mirror is not going to be worth very much, because you're not going to see any better than quite a few other places. Though you gather light very quickly.
Who in Edinburgh works on this?
I don't know names. I know the Royal Observatory on Edinburgh they have an instrumentation group that work on a number of these things.
Okay. I'll ask for contact up there. Thank you.
Oh, pretty good. Yeah.
Come on, Roger, you definitely want one of these telescopes, don't you?
He's very quiet, muted.
Oh, he's muted. Yeah, well,
I'll have two.
I'll have two. Yeah. One for every day and one for Sundays. Yeah.
Yeah.
but a lot of the astronomers also doing their PhDs, they talk about the excitement of going out to some of these sites. I suppose with bigger and bigger telescopes and more Zoom working, that's just become less and less frequent. And
Yeah. Well,
it's going to disappear, is it?
it's kind of disappearing anyway because you can't really have a 21-year-old postgraduate and fly them out to the ELT and say, there, go crazy. It's a billion euros of telescope there, so see what you can do. So they all have dedicated staff who work on these things. And if you're an astronomer, there is some sense in it's useful to be there in that you could make sort of real-time decisions and say, yeah, okay, that's good enough conditions, go. But they won't let you drive it around the sky and point it at things that it's a bit too expensive for that. So more and more it's kind of in what they call service mode, where you just put in a request and say, I want 2.5 hours on the Crab Nebula. The moon needs to be not in the sky, and the seeing has to be above this value, and it just sort of goes into the nil. And when those conditions come out and you're next in the queue, they will service that request. So it's a little more sort of automated. The other mode is visitor mode, where you actually turn up and say, right, let's go point it at this thing, and no, let's go over there, or that sort of thing. So they're trying to discourage that because it's not quite as efficient. And on some of the older telescopes, you can even turn up with your own instrument and say, right, I want it pointed there, and I want this thing I built bolted on the back of it, and let's go. Needless to say, that's not going to happen at the VLTs, though. So some of those on the Canary Islands, that I think they still allow some of that. That if you've got a particular instrument, or head of group or ex-head of group had a particular thing that picked up those planetary nebulas, the particular signature for those. So we had this thing that only picked up the wavelength planetary nebulas. So you put that on the back, and you could do sort of surveys of Andromeda, just picking out the planetary nebulas in Andromeda. So you would turn up with that and bolt it onto the back, but it was a relatively small telescope.
So in your career, Julian, what opportunities have you had, or are you purely on the number crunch? You don't actually.
Yeah, I kind of get to use big computers. So I got to use the 6th biggest computer in the world for a while. So that's my claim to fame. I got an entire talk on that. So you can have that one at your leisure sometime. But no, I've been waiting in case somebody gets a broken leg or something just as they're going off to the telescope. I'll step in and take your place, but it's never happened. And I'll say there are less and less opportunities now to go and do that, because they're all sort of staffed by service people who just do the requests for you now. And it is, I mean, there is some sort of adventure from that, but again, some of the people who do that, we had one guy who did a big survey in the infrared using one of the telescopes on Hawaii, and he went out to Hawaii like 4 or 5 times a year, and everybody said, oh, how exotic is that? And he said, it really isn't. You get to fly overnight to a long jet, you land in Hawaii, jet lagged to the eyes up. You then have to drive up a mountain. You have to stop halfway to acclimatize. And then the next night you have to drive the rest of the way. You then have to work through the night drinking coffee. You've got altitude sickness. You've got this constant throbbing headache. You're oxygen deprived, so you're not making some of the best decisions of your life either. And then you do that for 5 days, because that's all you've got, all the time you've got. And then you have to go back down, get on a plane and fly home. It's not as exciting as you think. In fact, yeah, Mike Merrifield, our one of our heads profs, he said, it's really weird what happened, because he spent quite a lot of time. He said, I was on one of these high up telescopes and I had to add 3 numbers together and take the average. So I added them up, took the average, thought that doesn't look right. So I added them up again and got a different average, and did it again, got a third one. So I thought, well, the obvious thing here now is to take the average of the averages, because that. The next day, when I got down to sea level, I was like, what was I thinking? And why couldn't I add up 3 numbers? It's just, it has a lot of good tales. So. Yeah, so it's not as thrilling as you might think, perhaps, some of these places. Although I would go in a heartbeat just for the experience. No, I get to go to big computers, but only virtually to those.
You could get to stay in that nice hotel in the Atacama and the Alma.
Oh yes, the James Bond one. Yeah. A couple of the people who used to work at Nottingham now work there. One of them works on the BLT4, and the other one used to work. She's now teaching at one of the universities in Chile. He's just in the last few weeks got to go back to the VLTs, because they've now come out of hibernation after COVID, and they weren't quite sure whether they were going to recover, because they had to shut them down in quite a hurry, and most of them, they'd never had their instruments shut down for 5 or 6 years. They'd been running continuously. They're all cooled by liquid nitrogen to get the best images they can, and sort of just switch everything off and run. So, but I think everything is back up and working now.
Excellent. Okay, any final questions before we close out the evening's questions and the talk?
Well, thank you very much for inviting me, and I think we're all due a drink now.
You especially. So thank you very much for your giving us your time and your wonderful talk on all the different telescopes from the ground upwards, and sort of giving us something to look forward to, especially things like Louvois, and maybe it'll get built,
Yes,
or maybe
it will.
American politicians will get in the way again, but you never know.
Who knows? Yes, watch this space.
But thank you very much. So that closes the formal part of this evening's talk. So you're free to run away now. If anyone wanted to hang around and have a chat about life, the universe and everything, or what we were doing, or ask some questions about Bath astronomers, feel free. But everyone else, there probably is a gin and tonic or a glass of red wine in Charles's case that needs you. So feel free to pop off, and even if it's Horlicks, you don't need to say,
Right.
then off you go. But thank you very much for everyone for coming along.
Thank you, Paul.
Thank you very much.
Thanks, Simon.
you.
Bye.
Cheers.
Thank
Bye.
you.
Thank you, Simon.
Thank you.